This video will be a very interesting video, I would imagine, for most viewers, even you guys that are not even into computer science or mathematics. It's just an interesting video to watch because just wait and see. All right, so one of the biggest problems in mathematics and especially theoretical computer science is whether the complexity class P is equivalent to the complexity class NP, or more formally, can a deterministic Turing machine in polynomial time be also the same problem, be solved by the non-deterministic Turing machine in polynomial time? Simply mean, can a problem be as quickly solved as it can be, verified or checked? Now, I've actually done some of my own research into this problem. I actually have a paper which is, I've been procrastinating on it like crazy. I mean, I've been working on it, a good, like over a dozen pages of, stuff, ideas behind the P versus NP problem. Now, P is conjectured not to equal NP. It's not really a resolved question. The reason why it's conjectured is because after many decades of research, you cannot not P algorithms are not found for NP problems. They're just it's just difficult to see. Nonetheless, there are some people who still believe that P does equal NP, and if P were to equal NP, if it's proved to equal NP, then a lot of encryption schemes, so especially RSA, which I'll get into in a minute, will become insecure because there will exist algorithms that can you can solve these problems, and people really have to rethink encryption. So P not equaling NP is a conjecture. People have have like a blanket of security because P equaling NP will be a huge big breakthrough in a complexity theory and a very interesting um, discovery for encryption cryptography, and see how do we go from there. Now, my own work is I looked at how we will look at trapdoor one-way functions. Now, one-way functions are basically they can be easily computed in one direction, not computed in the reverse. That's the intuitive notion behind it. And so now a trapdoor one-way function actually assumes knowledge that you like in an encryption scheme like M and N. The M and N are what I outlined was hidden. They are hidden from a potential attacker on the encryption system. And so, looking at this, how do we calculate the complexity of how long will it take for a guy, someone to try to decrypt the what I called the G function in my paper, and so how exactly will that work? Well, in the best case scenario, we're taking one step to verify that n plus n equals whatever they're trying to equal, but I mean, that's the absolute best case, and this is really pushing it because that's you have a better chance of winning the lottery every day of your life because because when you look at it, I defined it as M and N are members of the real numbers. You don't have to use integers. You can use 1.163792, going on forever and ever. But nonetheless, there still exists a chance that you can that you can crack it in one step. Now, the average case I would say is definitely exponential time at least, because the average case I did not find an effective or efficient for formally proven algorithm to find M and N in any given amount of time, because it's just members of real numbers. Computers can't really check the set of real numbers. It just can't be done. And obviously the worst case would be infinite or incomputable. Now this is definitely going along with the assumption that P does not equal NP, but this is not a formal proof because it's not formal proof because it's a trap door. Knowledge is a pre-assumed, so that's why it's not a formal proof of P not equal NP. However, if it was a one-way function without any prior knowledge, then this is a proof of P not equaling NP. So let's look at some non-trapdoor one-way functions and see if see some comparisons and similarities and contrasts. Now, RSA uses modular exponentiation. Now, modular arithmetic is pretty simple actually. It's not really hard to get. Basically, you have like let's just say our P is 12. P is supposed to be a prime number, but we're just going to say P is 12. And let's say we have 4 for G and 2 for A. It would be 16 mod 12. And the answer to that would be 4 because after the numbers reset themselves to 0 and then count again up to that, modular, base, I think is what it's called. All right, so anyway, so they use modular exponentiation. They use like tremendously large prime numbers, like really really large, therefore making them really difficult to decrypt. And so that's that is conjectured to be a one-way function because there's no formal proof that it can't be solved deterministically or quickly. But there's so far no one's been able to do it. at the same time, no one's been able to prove that you can't do it. So it's, again, a very famous and important conjecture as to, whether P does not equal NP. And again, as I said before, my example is a trapped one-way function. Therefore it's not a proof that P does not equal NP. But it's definitely going along the lines to say that P most likely is not equal to NP, because I would imagine that if you extend the idea of taking an infinite amount of time to other functions, and study I would imagine that complexity, which I'm going to do later. This will definitely, I would imagine, assist research into the P versus NP problem. Now, and also the Clay Mathematics Institute has offered a reward for $1 million to whoever can solve the problem. Now, you can solve by formally by dealing with the languages of P and NP, and however that has not been done so far. And there's actually a P versus NP page which has many papers like on some people say equal, some people say not equal, but really there's no like solid proof. I don't understand how these people can claim that they solve P not equaling NP if they're not millionaires, or there's not sort of like, why do they say it's equal? Like, where's the proof of P not equaling NP? Now, one-way function, on the other hand, imply that P is not equal to NP, because there are some problems which can be that can be solved quickly. I mean, sorry, verified quickly, but not solved quickly. And that the one-way functions are proofs of that, therefore implying P not equal NP. So I would imagine a stronger and a slightly more simpler way of going about P not equaling NP is proving that one-way functions do exist, and just universal, not trapdoor like my example is. Um, Also, previously I talked about the fact that there is a complexity class FP, which is like the function problems of polynomial time. And if that equals FNP, the function problems of NP class, then that implies P not equal NP. So if FP equals FNP, then P equals NP. It also stands to reason that if FP does not equal FNP, then P does not equal NP. That's another way you can go about doing it. But nonetheless, it's for $1 million. So whoever can solve it, that's not a small amount of cash. And so that is all for this video. Hope you guys enjoyed the P versus NP problem, and that's all for now. See you guys later.